So I would like to first of all just do a wee quick run through of what the Master Series is all about. Very quickly, in the Master Series we have three product ranges. We have the big building design suite, we have the lighter PowerPad suite, and then we have your custom only take what you need suite. All three of these can handle concrete. So looking at the building design suite, you have your analysis center, your BIM integration, and that is the core of the building design suite. You can add on dynamic and finite elements if you wish, and then you can also add on your concrete design. So your timber, your steel, your connections, and all the other ancillaries. So what we'll be looking at is the modeling and concrete design inside the building design suite. So that's our option inside the building design suite for doing concrete design. We will also be looking at finite elements, and the finite elements add-on, which will add on to this or the PowerPad, will allow you to do flat slabs, transfer slabs, shear walls and rafts. If we're talking a PowerPad scenario, we will have our 100 member frames, and again we will have our concrete design. We do also have little standalone modules as well. So from a concrete point of view, you would have retaining walls in that and pile caps. We will not be looking at those two programs today. So we'll be looking at the concrete with its frame analysis. The third option is build your own system. So there's several ways of doing concrete if it's just concrete you want to look at. And that would be with a frame analysis plus concrete, so that one and that one. Or you could have the simple beam design, which has its own built-in concrete, or the PowerPad. But then again, we're back to the PowerPad itself. So there are several different ways that you can do your concrete design, and as you can see, all these individual modules, they all interconnect. And this will be a typical system that somebody might set up in a larger organization. And I'll just click through all the buttons first just to get them on the screen. So they have 8 frame analysis building design suite, but they have 2 concrete design, and in their case they do a lot of composite, of 6 composite and 4 steel. So the beauty about the Master Series is you don't need to buy 8 of everything. You can have 2 of that, 4 of that, 1 of that, 6 of that. It is all customizable by yourself. Okay, I have one more document to show you before I actually start and use the program. And this is a little document put together this morning on concrete design. So what are your options? Well, the first option is for just doing simple single span beams. There is a free version of the Master Series which you can obtain from the website. If you went back to our website, there we are, and you just went search and you typed in free, you would find the single concrete beam designer as well as its friend, the steel one. We also then, for just doing simple beams, we can either go for the commercial version of that beam designer, which can handle up to 16 spans continuous beams in concrete and gives you all the details and everything and the scheduling. Or we could use the MasterFrame and the concrete beam design, again to do concrete beams. For frames, we're either looking at the PowerPad 500, or this building design suite. The MasterFrame is also there available for you if you want to do the concrete design. And as I said earlier, we can add in the finer elements if we so wish to do transfer slabs, flat slabs, the lot. And as I said earlier, we will not be covering retaining walls and pile caps. So just closing that down and just minimizing this, What I'm going to do first of all is some simple concrete beams, continuous beams, simply supported beams. So I don't need the big frame analysis. I can go into the designer suite, into the concrete beam designer. And what I can do first of all is I can come to my library of sections or of files, and I can choose a 2-span with a right cantilever. And I can say get that. And of course the first thing I should always do is to save as, and I'm going to save it back into my main directory, and I'm going to call it right cantilever demo. So I'm going to save and continue with the new file in the new location so I don't destroy my library file. So what have I got? I've got 2 spans. Well, I could always insert a span, and I've now got 3 spans. 1, 2, 3. I'm going to make that second span 6.8 meters, and they all have the same section size and the same basic loading. But let's put this loading down to basic per meter squared. So I'm going to say the dead load from the slab is 4.8, and take that out. The live load is going to be 4, and take that out. And I'm going to do alternate loading patterns, and we are, yes, working to the Euro code, but I'm also going to tell it that I'm working with a spacing between the slabs of 4.5 meters. So it's going to magnify those loads up for me automatically. I can put on point loads and varying loads. There's a very good webinar just on the simple beam design. I'm not going to go into that today. So what can we see? We can see our bending moments, and we're looking at our different cases, and we can see our deflections over here as well for our different cases. Obviously we did tell it that the last span was a cantilever, so this is our cantilever. And let's just increase the scale of that, and you'll see that we are getting this small fixed value of moment due to the cantilever, whereas in this span we're just doing a straight hog between the two. So very simply we go into design, concrete design, and here we go. It's giving me a suggestion of reinforcement. Now 750 deep, so it's suggesting we have to have sidebars, and there we go, the sidebars. It's also suggesting that we're going to use 420s, and we're going to use 2 pairs of bars in the middle here to satisfy that. Now the nice thing, simple thing is I can remove bars by right and left mouse clicking. I haven't actually done much design here yet, so 3/16 would work just, and I can come down here and I could see that 3/16 would not be working, so it needs to have the 320s. And then this is obviously just the enhancement to the Eurocode due to the lapping. So at the very support we're getting the 420s working, and I prefer to see 16s in there and 16s at the other end. Now in here I can turn around and say 16s, 16s and 16s. So that's all nice and clear. And I come along to the next span. It's a rectangular section obviously, and I can see that I'm beginning to get this hugging. Now the difference between BS and Eurocode, for those who are unfamiliar, is in the BS we deal with bending moment diagrams. In the Eurocode we deal with a force diagram, but that is distorted then by this shear drag that's also then applied to the members to distort that, but the shear drag never gets bigger than the support maximum moment, so the shear drag can't get bigger, so it would normally tail off in a more hyperbolic shape there, but it doesn't in this case. So I'm going to have to say no, I can't have 320s. I'm going to have 4/16s and 4/16s top bottom. So that's coming through from the other span. 4/16s is fine, and we're just lapping those without continuing, with 2 points. And this third span then we're going to have to put some bars in on the right hand side because I added in an additional set of information and add in another set bottom. So they're now lapping and everything is looking good. 4/16s, we could possibly come down to 4/12s if you want, maybe not, 4/16s on the bottom. So I'm going to go back into detail in this in about 5 minutes when I come in with a frame analysis package. So that is how simple it is to work in concrete design in the Beam Designer. Simple, isolated, simply supported, continuous cantilever beams. We can also work if we have a subframe and introduce columns above and columns below. So if I said I have a 3.25 columns below and I want upper columns and they're also 3.5 high, it will actually affect the moments that we get. So we're getting 194 and 237, so they're not symmetrical because some of it is being resisted by that column. So take out my columns and the forces start to change, and take out the height above and the force comes down and it evens itself out instead. So simple beams done. What I'd now like to look at is some beams, concrete design and frames. So into MasterFrame, and if we're using the building design suite or PowerPad, we are still going into MasterFrame because MasterFrame is just part of those programs. It's the analysis component of those programs. So Tommy's demo files, concrete demos, and we can see some typical concrete, simple and more complex frames, and we will look at a more complex one in a wee while. I'm going to come back and take this simple plain frame. Now, the things we have to remember is, turning off my nodes, I'm just putting in the front view, is loading. The difference between this and normal steel design is in steel design you're normally simply supported and therefore determinate, and you don't have to worry about additional loading patterning. In concrete or in rigid steel, to be honest, you would have to. So let's first of all look at our loading, and here we go is our total load, and let's look at the loading on a particular loading case. All spans loaded, and then we have maximum, minimum, maximum, and that's the minimum on this floor, maximum on this floor. So we've got one set of maximums, and then we have the alternates done for you. Very, very simply. Now, what I suggest is you also have the serviceabilities of those, and I like to actually think that something like this would be saved for use over and over again, particularly in the loading combinations. So I'm going to go File, Save As, and I'm going to save it as a standard EC2 load pattern. So I'm going to save that, and I'm going to save that as a backup file, so I'm not going to modify what I'm working with, but that may come into use at a later stage. So if we go into our loads, obviously the loading on the frames is very important, and we come down to member loading. Very simply, we have a dead and a live load on each of the spans, and to allow us to do that patterning that we did earlier, we're designating these to be dead 1 and live 1, whereas these are dead 2 and live 2, back to dead 1, live 1, and dead 2, live 2. So very simply, easy to perform, and likewise up here. Now the values can be different, and let us put an additional point load, say for example on this span. So come along and take a point load, and we're going to put it in as a dead load, so it'll be in the D1 group, and we're going to make this 18 kilonewtons, so it's a big thick wall, and we're going to put this at 4 meters along the member. So point load there on that member. Very simple. You have these three basic loads, but you also have all of these additional loads for giving you unusual shapes. Now most of these would not be required because that will cover them, but you then have things like thermal expansion, shortening, and off-center torsion on the member. So if you're doing an edge beam, you can apply loads off the flange and put a torsion onto the member. All very, very powerful. So the loading cases, again, very simple. If we look at the loading cases, I have them already set up for us with the 1.25s rather than the 1.35s because we're in the UK and we do that for certain types of structures. But the important thing is for each of these cases, what's the load factor? So we're saying in case 1, which was all spans loaded, and just to make things look sensible, let's put on the diagram. We can see with our big horrible point load, our dead and live maximum of all spans. The second one is alternate 1, so maximum minimum, and we'd achieve that by making the D1 L1s to their maximum, and the D2 in the Eurocode will be the same as the D1. It's just the L2 that is now vacant from the member. So maximum live load, no live load, maximum live load. And to be honest, it's a more sensible approach they're taking here, one of the few in the Eurocode, that if it's a permanent load, how can it be patterned? Obviously, in some certain instances, you may wish to pattern that a wee bit more down to 1.0 or 0.9, but not necessary for most. So there's the loading combinations, and then there's the serviceability equivalence if I want to do my foundations. Okay, that is load patterns, loading, section sizes. Well, let's just look at what we can apply section wise. These are T-beams, and they're all T-beams. These are in fact inverted T-beams, just to make life fun and to demonstrate one or two things. We have some square columns, and these are all square columns by the looks of them. I am going to make that one into a round column, so a 300 round instead of square, just for the fun of it. You do also have all your steel sections and things like that, but we're concentrating on concrete. So let's just go and analyze this. Static analysis. And we'll do it as a plane frame. We've also applied notional horizontal forces because in theory you should do. And plane frame. So there's a wee bit of a horizontal push just to get an additional set of moments into the frame. Okay, now results. Well, the results are no different from any other program in that you have your tabular results, your deflections, your moments, your reactions. More important is your graphical results. And we will see, if you look at our bending moment diagrams, put this in the front, and just for those who are still at college and looking at this, if you watch the moments here at this point, and we'll show them, and we'll show them for major axes only. So that value of 338 is the moment due to the dead and live load maximum on all spans, and likewise that's 382. So remember those two values. If I then look at a different loading case, you'll see that that goes down and then it comes back up again. It comes up to a slightly higher value because of the alternate loading, and in this case actually the column is probably causing it not to go down as far. But if you remember here, we were 407, whereas initially under all spans loaded it was only 382. So this span, when we have less load on that span, drops and has additional moment, so therefore we need additional steel. We also can look at deflected shapes. That will be for the gross section, and we can also look at shear diagrams, and in our case we're getting these big shears from those loads. Just take off the values there, and I'm going to go straight now into concrete. So I'm going to go back into concrete. I'm going to spend about 10-15 minutes on this concrete design, and then we're going to look at a big 3D frame with FE surfaces. So design, concrete, beam column and pad design. So we're going to look again at our diagrams, and we can see here we've got an awful lot of reinforcement. We're playing around with 2 layers of reinforcement in this case, and again playing around. Due to my changes, I now need to have another bar in here. So all I'm needing to do is to use my mouse and left and right click to increase, decrease or remove. So left mouse increases, so 320s or 420s. 416s isn't going to do it. They are probably wanting to use 3 bar arrangements. So down to 3, up to 20s, and we're just working. But we do have a problem here due to the kicks in moment that we need to sort out here. And we're going to turn around and we're going to stretch these bars, and we're going to make them, and I'm going to stretch both of them at once. So I use the lasso to stretch both of these out past that point, and therefore it now solves the problem. As again, remember we're in Eurocode, so when we move things it does change it slightly more than you would have thought, and push that. So moving along, we'll see that the next span we do need to maybe go up to 16s. The alternative to going up to 16 from 16s to 20s would be to redistribute. And redistributing moments, we handle it in a very, very powerful way. We don't just say, oh, put 20% there. We say, well, what do you need? How much redistribution do you need? And you'll see from this little dotted or grey line that we already have some redistribution applied, and it is 10%. So I'm going to increase that to 15, 20, 25. Let's go all the way up to 30%. 30%, those 320s would work, and just work in here, although I'd be happier in here with 325s or 216s and a 20, something like that. It's very close, but you know, it works. All we need to do is to take this bar and increase its length ever so slightly, and that now works as a concrete design. And obviously what we do on one side, then we really should rebalance with a redistribution on the other side. So 30%, it's not happy with its bottom steel. I'm trying to find it, bottom steel. I'm going to make into 25s. Remember, I put that big point load, so we're going to go with 325s. And do I need the other 16? Yes, I do. I need something to either go up or add in another bar. So I'm going to add in another bottom middle bar, and I'm also going to take that bar and I'm going to move it into a different layer. So that's come into the inner layer, and I'm going to reduce that down to 16s, and I would probably get away with 2 of them, or maybe even 1 in the middle, but to be honest it would make more sense to have them in the outside as a pair. So looking at this, and just expand that a second, we can see our bottom bars and our inner B2 layer bars of 2 16s, and that is now all working. So detailed design of concrete beams. Some of the things we can do are quite useful. We can actually take a design from a beam and copy it to another one to try and make the cage work over and over again. And if you took that reinforcement, you wouldn't want to copy it there because it's going to fail. So in this case, we're not going to do the copying. And I'm going to take this. I know we've done a rectangular section there, an L there, and a T there, just for the fun of it to see what would happen. So if I take this reinforcement, which is just about working, there we go, it's working now. I could then come along and say copy bars and links to that span, and I would then see if that steel works in this span, and back to the members again, and we can see that it didn't, so we would actually have to go for similar to the other 320s and maybe not as that at all. So here we would need to again increase that also to 20s. A wee bit of redistribution would solve that one for us. So on the beam data we can go and say give us 10%. So we only need to push 10% in and not penalize us in the bottom, and then we're coming along and we'll be putting 10% on the right hand side as well. And we'll see that solved our problem without having to go to a more additional steel. So that's our beams. We also can do the columns, so little square columns, very simply, and it's classified as slender, and it's looking using the K1 K2 factor for its effective lengths and classification as recommended in the National Annex, because there is no guidance in the Eurocode itself. So we're slender. So this is our axial capacity of 3,200, but we then have moments in the X and Y. So we have out of plane moments as nominal moments to allow for, and our deflection moments. So we need to then look at it uniaxial in the X, so only X moment, and then also only Y moment, and then biaxial with dominant X and biaxial with dominant Y. So we've checked all 4 different permutations plus a shear check for ourselves to make sure that this works. If I remember, we did this one as a column, a circular column, and again it's coming in as slender due to the effective length functions, which is quite onerous. And this one, well, this one's not happy. And why is it not happy? Because somebody was playing around with the reinforcement, and we now have too much reinforcement. Of course we got too much reinforcement. Let's drop those down to 25s and 20s. Now we are working because we're within a distance from a restrained bar for these unrestrained bars. I would much prefer to see it a symmetrical reinforcement and symmetrical 16s in the corners, 20s in the 12s in the edges. But as you can see, we can go just purely for 20s, simpler cage, and away you go. And again, we're looking at this because we're in slender members due to some components of our design. We do need to put in more onerous reinforcement. Okay, now pad foundations in a small frame like this sounds good to me. So first of all, a question from our defaults is, what pad do we use? Excuse me 1 second. That's better. We're going to use C3240 concrete. We're going to use a 10 kilonewton surcharge from soil and whatever on the pad, and we're going to work with a safe working pressure of 200. So let's reduce that down to 150. Obviously everything changes, and we also have a density and a height of bearing of the look. So we now need to make this work. We're only 178 kilonewtons per meter squared we can only allow, and the surcharge plus the depth gives us an increase in capacity that we can actually work with a safe working pressure of 176. So 179 is just over the limit. So either we widen this to 225 by 225. There we go. Coincidental, not my setting up of it. And we can see that it all works. Now, it's quite a small pad. So in reality, this punching shear perimeter will take place, but this outer one may not take place. It may decide to go, well, actually, I could go out this side, or I could go out two sides, or I could just shear straight across the face. So we check all of the different permutations. So we're looking at our shear, that's our beam shear straight across in each side, upper, lower, left and right, and we check this at D from the column face. We check it against the column face as well, and then we do our column head punching shear, so we're doing our detailed checks there, and then finally we're looking to find at D, 1D and at 2D what are the weakest. The weakest ones are the ones with the highest stress. So that's the full perimeter, and then with the others, and we'll see that we have no problems whatsoever with our punching shear. If I was to come along and take this column and say, well, actually in here, due to something, we need to move this off center. So the 0 means it's centered, so I'm going to say it's going to be centered actually only at 500 from one side. 500 from one side causes obviously some pressure problems, but more importantly, it could start to annoy the punching shear as well. And in this case, we're getting column face moments and things like that. And even in this case, the starter bars aren't long enough to actually facilitate the design. So 500, we couldn't do 500 with those starter bars that are 20 mil bars at that depth. So we either need to have bigger depths or do something about it. But if I say make this 700, then we should find one or two of the errors goes away, and the punching shear is in this case still okay. But it is just the pressure now due to it being asymmetrical on the base that is a problem, and we can be asymmetry on both directions if we so desired. And again, that increases the applied moments under a partial area again for you. So that's beams, columns, pad foundations. Now we're halfway through. What I want to do now is to exit and load in a big frame. So I'm going to open. In fact, if I go to recent files, I can choose this big file. Now, if we're in the building designer suite or big MasterFrame and we're doing a 3D frame with area loading, that process does not change. The only thing that people will ask me is, well, Tommy, how would you do pattern loading? Now, in this frame, we are in fact only got a concrete substructure plus a transfer slab, because these columns here don't come in at the same point as the columns underneath. However, if I was to take one of the upper levels, we can apply area loadings as alternate loading patterns as well, and it's quite straightforward to do so, in that you're just choosing the members for the D1L1 group and the members for the D2L2 group, and I will explain this by doing this actually in the flat slab. It's the same principle, and it will know to then pattern the loading. So rather than doing it in here, I'm going to go to my plan at level 1. That's my flat slab. Turn off the 3D. So what have I got? I have got my columns above and below. So below, above, above, ouch. And I've all these intermediate internal members. Now, if I was doing a flat slab and not wanting to do pattern loading, then I wouldn't need to have any of these internal members, just the column node points interfacing. But the reason I want to do pattern loading is because if we look not at the surface definition, but at the load patterns on this big surface, we will see that I have given it load set 1, which is in fact D1 L1s, and these are the panels now. That's because that is a lift shaft and that's a lift shaft. So I've created these internal members which will fall out in the FE themselves. They'll just be used for defining the patterns. To do that plus that, so we can do a D1 L1 and D2 L2 loading patterns, and we can get our lovely increased sagging moments. But we also need to think about doing that in the opposite direction. So we create a set 3 and a set 4 so to give us our patterns. We don't have a 5, 6, 7, 8 or 9. They're in there because we just decided to give you 10 patterns just in case you're going to play weird things on us. So what does that do? Well, those patterns are then used if we look at the loading cases and we come down not to the composite and the wind loading cases, but to my pure concrete design cases. I have a FEA live 1 max, live 2 min, so max min. If I then look at the again, I have a min and max. Or if I go to my permutations and look at them, I have dead loads and then maximum only on my L1. Now the other thing we don't do is we don't invoke all 4 groups. It's either east, west or north, south. It's never both. Otherwise you'd end up with double the load. So this is going to give me my patterning and then my other pattern. So that's those 2. And then in the opposite direction, the L3s and L4s are doing that. The D1 is basically to do with the self weight of the slab, and the D1, 2, 3 and 4 are for additional dead loads. So the D0 is basically your self weights, and it says self weight in here, so that's what we would use that for normally. So that allows us to do the patterning very, very simply. Now the FEA is again very easily set up. So we edit our surface, we define a perimeter for the surface very simply, and it's not difficult to come along and say that I want it to go to there. Instead, obviously it doesn't like it crossing itself in this case, so maybe I won't do that, and therefore it's now happy. If I wanted to, I could create an internal opening by just choosing the members I want to be the internal opening. So I could say that's an opening, so when I return to the main border it's now an opening, but in my case no, it's not. Edge conditions, there are none because this is a slab supported by something else. If this was a raft foundation, I would turn around and say, yeah, it's a raft foundation with a spring stiffness of, and give it a 10,000 kilonewtons per meter cubed subgrade modulus, and also compression only if I wanted to allow uplift. What I have done is I've applied loading, just a simple live load, which is an alternate load set. So rather than saying it's in load case 1 or L1 or L2, it's locase alternate. So it now knows to look at that pattern I had defined earlier and go and do its loading. This will all be apparent very shortly when we look at the results. And I've put on an additional dead load of 1 kilonewton as an additional load, and that will be patterned as required. So now, last thing I've done, just to demonstrate, is I've created 2 attached beams, and I've said that those beams are attached to the bottom of the slab, and I've said that we'll use the combined plate forces and we'll use the flange widths of concrete beams. So we'll classify the width according to its span each time. And that's my attached beams. So that's my little FE slab. And if I look at it in 3D, put it and start to rotate up, you will see the 2 attached beams here. Now, the trick with the attached beams is you define it as a rectangular beam, and you only define the depth that's actually projecting below the slab. So that is a 1 meter by 300 deep drop beam. So the web is 1 meter wide by 300 deep. If I was to go and say section sizes, I tell a lie, it's only 200 deep. So that is how we do these. We don't define them as their full depth, we don't define them as T's, we define them as the bit that's glued onto the bottom or the top of the member. So there we go. But we have more than just the one FE surface. If I went back out to full frame, we also did FE surfaces for our lift shafts at each level. So we've got a wee bit of interaction here. So we'll now go and analyze. And I hear you saying, but what about the mesh? Well, it'll actually do its own meshing. And yes, I've been twiddling, so it wants to redo a mesh. And it will just use a default, and the default is 1 meter. You don't necessarily need to go any deep denser than that unless you're getting errors in your analysis. So we've done our analysis, we're all happy here, and we're working well. And if I then go into results, graphical results, bending moment diagrams, only in the main members, not interested. Deflections, mainly the main members, but a wee bit of the FE as well will actually show up deflections. So if you're really interested, so we do actually have a wee bit of steel structure that maybe needs stronger beams. It's one case, but it's not affecting our slab design at this point in time. The loads are being transferred, so that's for a steel design webinar to go back and fix those and get those members not being bits of plastic but strong members. So now I'm going to go to shell elements, and here we see immediately some nice pretty diagrams. Now I'm going to initially forget about the 2 columns and just come straight to planet level 1. So there we go, there is our little FE surface, and now it's taking those upper and lower, and I'm just going to refine that view very gently and just do that. So windowed that, and it's taking us just with the FE. So we can see our major displacements here, not so much here, due to those upper columns that don't transfer, that have to go through this transfer beam. Now over here and here it's not as bad because we do have the transfer beams in here. It's just the slab doing all the work. So the first thing you do is look at our maximum errors, and if I look maximum errors, I've got massive errors here and I've got some errors around here and here. I like to see a lot of blue. Those values, 5, 8, 9, 10 isn't that much of an error really. It's not as direct to the final moments as you would think. So what we want to do is to nip back out and say, well, my little coarse mesh isn't that brilliant. So, or is it under analysis? There we go, FE analysis. Sorry, this did change. So I'm going to go and put in some local mesh intensities. That's better. And I'm going to say that I want the mesh down to 0.25 for a radius of, it should be about 3.5, 2 meters, 2.5 meters. So now I'm going to say, apply that to that, all of those, and all of those, which were critical. And we had problems here, and we had problems around here. Now I just increase my dot size so you can all see that and go for that. So I'm going to do all of those as a finer resolution. Now I think I had a wee bit of problem back there, but I'm going to leave those. Oh, and I did those too as well. So reanalyze, static, absolutely remesh because we've got new details. Yes. So it's done the remeshing automatically, very smartly. So space frame analysis won't take long. Let's again just zoom that back in. That should zoom quite clearly. And now results, graphical results, elements. And there we see we're getting a lot more blue, very little green. There's a wee bit more green, so maybe we should go for each of these points and do that higher resolution of mesh. But there's very little, and those are acceptable around these nodes. Just from inspection, but around here, yes, I would probably prefer to see these again also meshed to the finer mesh. So we've done our checking of errors. What can we look at? Well, membranes, not really interested. MX, and we're not seeing much. Now, first of all, there's a whole lot of horrible hatching here, and I'm just going to go into the viewing dialog and go into the finite element display, and I'm going to say don't show the mesh itself, so we can see a wee bit clearer what's happening. Back to my graphics, put it in plan, and we'll see that everything has been sucked up by the columns as you expect. Now if I was to go to 30, I can still see it's nearly all, and I can't tell the difference between any of these. If I then go, say, to wooden armor moments, we see a wee bit more. So the wooden armor moments are the more applicable moments for doing our design. And so we're looking at the MRX. Now, we need to see what direction that is. And there's X. So it's the moment bending about that member. So if you put a line through that, it's bending across that. So it's the steel that's going to be running in this direction. So we can see where we have these point loads coming down onto our slabs, we are not happy. But we can also see that we're getting swallowed up in these wee point loads around supports. So what I can do is I can turn on peak smoothing, and I'm going to say it's at 0.3 of a meter and apply that. But that's just for that one loading case. So let's go and look at my ultimate limit wooden armor moments. So here we can see a wee bit more detail. Here's my positive values, and there's my negative values. So we're seeing that for that. More importantly, if I was to come back and look at that, not for the envelope, but for just my FEA surfaces, we will see what we saw previously. But when we start to look at the pattern loading, we can see this patterning coming in that we weren't seeing previously. So we can see this patterning coming in, and then in the other direction, which has very little. Now, we don't see anything in this direction because we're looking at MRX when we're actually really expecting an MRY value. So let's change it from MRX to MRY, and there we go. We see this patterning coming through on case 24 and on case 23 to a lesser extent. So that's giving us the maximum sagging moments on our frame. So the next stage you want to look at is steel. So we can turn around and say, right, let's look at our ultimate cases. And here's all the top steel we need in the x-axis. So steel running in that direction is what we need. And it's quite a lot, from 0 all the way up to 4.7, which is a bit too much. What I would do is a couple of things. I would drop this to 3, and then I'm going to apply the peak smoothing, and I'm going to say that I want to use contour values, and I'm going to use contour values based around rebar. So I'm going to say at 2400, at 1500 and 1000, and apply, and that will give me where I need. So I don't need more than 16s at 100 except in these very high intensity areas, which I will then, because that's a point load, so we need to get some additional rebar in this direction to support that, and likewise at these values. That's X. Y is sort of similar. And then if we look at the bottom reinforcement makes more sense to us. So again, I have already set up some parameters. So I've set up to 2.4. So there's only a few wee areas that are significant that I would need to put additional reinforcement in. And then the bottom Y. And again, we're not, other than it's suggesting we are hitting over the 12,000, but that's in such a small, minuscule location that we're not actually even going to worry about that. So I could turn around and say, well, actually, my maximum is going to be out to, say, 4500, and apply. And you'll see there's very little difference. It's just that little area and that one that may need additional bottom steel to counteract that. Now, that's doing it this way. One of the things that people aren't able to do using this is banding and averaging, because a moment at one point isn't what you would design for, because you're going to design for the average over a width. So if I go to strips instead, I am able to take, and it looks better now in 3D. This is MRY moments. So we're looking at MRY. We can see a hugging of 426. I can come along and say, well, actually, rather than 426, which is the unique peak value, let us average that out over 1 meter. And that drops down to 350. Now, in the BS and Eurocode, we can actually take it even wider than that. Now, and I was just looking at the Eurocode regulations today, and I couldn't see anything. Obviously, you'd consider a column strip to be half the width, a quarter either side of the column, of the span, of the shorter of the two spans. So we're basically, with our columns underneath, on a 4 by 5 meter grid, which means that we could take a 2 meter width. Now, if it was BS, you would take that 2 meter width, but you would design the 1 meter width for its reinforcement, and then the other 2.5 meters external to that for a different reinforcement. I could not see anything in the Eurocode that said you needed to do that restriction. So if we are able to not design the 1 meter width but the full 2 meter column width, then we actually drop down again from 470, 350 to 76. So we're taking a width of of design, we're able to get a more average reinforcement. Obviously, under such quite high point loads, you may want to consider other things. Now that's done on one. I can do it on the next. Just turn on averaging and go for 2. And on the next, whoops, sorry, wrong button. Yeah, line 3, averaging, turn it on. And is there a fourth one? There's not. So I'm going to add in a fourth one myself. I'm going to say it goes from this node to that node. And it will be strip averaged at 2 meters and apply. And there it comes. Now, each one of those individual diagrams is very useful, nice to see, but it will be even nicer if we could see them all. So let's show all the diagrams in that current group of MRY, and it said 1 meter, it's now 2 meter strips. So there's my MRY moments, and you can see we have very little here because we have our big beams, our drop beams are taking out most of those sagging, hugging moments. And then we can look at the next strip. So we can actually take this and then say, right, let's look at the MRX. So that's the ones in this direction. It's doing some calculations, as you can imagine, and it's basing it on some strip averages. So if I go like that, you'll see that you've got a strip and then another strip where you have an additional, and then another strip. Now in reality, that's a sagging mid-span strip, and that's the hugging over the columns, because that's columns from above rather than from below. So it's this one and this one, but that is still a useful bit of information. Now you'll notice that we actually take the strip past the edge of the member. That doesn't matter. Even though that's 2 meters wide and only 1 meter of it is concrete, it will turn around and say, well, actually, I'll base it just on that 1 meter. So we're not over or under egging the results. We're actually still giving you the correct answers. And I apologize, the phones must be busy there, so I apologize for that ring. So that is our concrete design. Now, obviously there are 1 or 2 other issues. This is a program for doing finite element analysis, and the design of the concrete for bending is an additional component of that, and it's something that our users use very, very happily. What we weren't able to do is, other than look at some stresses around columns, we at the moment would have to go and just do a manual check on the punching shear around the column heads, and I know somebody has asked about that. And personally at the moment there are 1 or 2 reasonably respectable spreadsheets out there by the Concrete Society that will allow you just to take what the reaction was in that column and what the area, the loading is on the floor, and do your punching shear checks very, very quickly. So they asked about deflections. Now, if I come back into my properties of my surface, we will see under material we also have a material factor. So we could turn around and say that all material factors for all surface cases should be based on cracked or uncracked with short-term creep, or the worst of the worst of the worst is cracked long-term creep. And that takes your Young's modulus down to 0.167 for your serviceability loading cases, and thus gives you a very realistic deflection on your members, on your slabs. So we could do that and reanalyze, or most people are happy to do 0.5 or 0.25. The other is a very onerous check on long-term loading. So that is the different aspects of designing concrete frames in the MasterSeries. Now, I have some questions, and some of the questions are very, very useful, so I'm going to go back through them, because if I go into the frame I did last in just general frame analysis, when we set up the concrete design and we go into the concrete design, we're able to set different parameters. So, I mean, there's over 100 parameters here. What are our rules for auto design? What are our covers? 30 all round, pads 50, columns 30. What are our assumptions for columns? And we're going to assume that they are restrained deep. We could assume that they are braced. And we would have got our columns out a lot better. And yes, it's braced by those two shear towers, so it probably is braced a lot more than we thought. Again, pads, what are our assumptions? And methods of detailing. But one of the things you can then do with this is you could save this as a default file. So I'm going to save this as multi-story and save that. That means I can come in and pull all those settings, all those hundreds of settings in again and again and again. Now, the other nice thing is that every time you use one of those, if you then go to a brand new file and has never seen concrete before, it will use that previous set anyway. So that is a very, very powerful tool. How do you remove a load from the frame? Right, we're getting down to the basics of MasterFrame. I don't mind hanging on and recording these for you. If we go to loads, member loading, and take any member, take that one. If you want to get rid of that load, you could either set the value to 0, which will do it, but it's a fix, fiddle, or you can come down and say kill, delete that current load, and there it's gone. Now, somebody else, while we were here, asked, how can I copy a load to several members? Well, if you take that previously done point load, and I go to that point load, so let's want to put a point load onto this member, and this one, well, it's pattern loading, so we're going to say that one and that one, that one and that one, and then those two as well, but with a different load factor. So what I would do is I would go to copy mode. In copy mode, I can kill everything on the current palette. It's not affecting any members. I can grab my load. I'm going to call it D1. I'm going to make it 18. And I'm going to put it at 4 meters. Now, let's display my load diagrams. And back to my editor. So, this is my load. It doesn't appear anywhere. So I can go and say there and there, and I can just go window, window, those two. Obviously, that's from that point there, and that's from that one. So we might need to rearrange those. If I wanted to put that onto those two, I would need to change the load group to 2, and then copy that onto those. If conversely somebody decided that the dead load was now different, and I would go to global editing, and I can see for any member what the global loads on that are, and I can see I've got 4.8 and 4 here, but I've only got 2.5 live on those, and I'm going to say actually I would much prefer those to be 2.5 live everywhere. So I'm just turn off the load diagram for the time being. Didn't mean to do that, sorry. Member loading. Right, so global on these two, that one and that one, and I can turn around now and say I want that to be, we'll not make it the same, we'll make it 5.5. And if we look at this one, they were the same, but they're not. I'm silly, because one's a D1 and the other's D2. Yes, so they will never be matching 5.5. That's the problem. But if I was to say I wanted to make the basic load from 4 down to 3, what I can then do is I would actually be better to go for single load, find my live load of 4 and increase that on all those members to 4.5, and then find its L2 component and make that also 4.5. And that's how simple it is. Is load patterning on beam setup similarly to floor slabs? Well, FEA slabs, because we're dealing with whole surfaces, handle them slightly differently. If you're dealing with normal frames, and if let's go in and find ourselves a 3D frame that's not plain frame but is something a wee bit bigger. No, let's go for typical frames. Da, 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 da. And I try to find a frame and I'm struggling. Well, no. I think I need to go into Building Designer Suite. Well, let's just take this one for example. This is area loading on it. So we're sort of stepping outside the concrete brief, but if it was a concrete frame without FEA, this would still apply. And when you go into your loads and your area loading, edit panel loads. So you've said in your groupage for FEA, or not for FEA, for normal area loading, that you're going to have X kilonewton per meter square. And we only allow you to say what's the dead and what's the live. We don't tell you whether it's dead 1 or dead 2, live 1, live 2, live 5, live 4. And the reason for that is by default, generally, you're dealing with simply supported members, and therefore it doesn't matter. However, we do have recourse, and let's now just come down to level 1 to actually allow you to do pattern loading. So if you can think, if these were actually continuous beams across here, you would need to consider max, min, max, min, max, min. So what you would need to do is, just like in the FEA, set up, oh, somebody's done it. Thank goodness. Some dead and live groups for group 1. So we've got those, and I would probably suggest we would put those 2 in as well. And then the D2s would be the opposites. And then we don't have L1s and L2s because the loading is all spanning in one direction, so that is how it's going to be loaded. Now, all you then need to do, because you've told it that these members, that dead load is always D2 and that live load is always L2, you need to then set the loading cases. So loading cases, if we look at this frame and look at the loading combinations, we have set up the loads twice in here. If you look at the next one, we've set them up twice. Now those are defaults for self weights. So everything's been done twice. Now we're looking at dead plus live, but in fact it's only done it for one set. So in reality, he is not going to get his patterns. So what he would need to do, because this is just somebody playing around demonstrating, what you need to do is say, well, right, we also need the 1.2 here, 5 and 1.5. And we then just need to make those all the same, but we then need to introduce the patterned ones. So the best way to do that, for me, is under loading cases, is to import cases from another file. So if I remember, I think I stored it here. There's the FE load patterns that we did previously. I think, yes, standard EC. So I put it into concrete, I can now say I want to import, and what I want to import is those six loading cases, and import those 6 cases. So I now have 6 additional loading cases just to make sure I've got the patterns right. So go to all spans loaded, and then we have alternate 1, alternate 2, serviceability alternate 1, alternate 2, and then all done and back to 0. So we can do it that way. We can create your own and bring them in to use over and over and over again. What wasn't included in those was the D1, the D0, so 1.25 there and 1.25 and 1.25, and then the last 3, that's going to be ones. And we actually have an option to add or remove a load group in multiple cases, so I can say in these last 3, control and highlight them, I want the D0 to be 1 and apply. So when I go to my combinations, you'll see that they're all now 1s. So I actually added that in quickly doing that. I'd like to thank you all and wish you all a very good day. Thank you and goodbye.